Hello, everyone. Welcome to my YouTube channel. In the previous session, I have discussed the paper 9701, winter 23 question, paper 22, question number 1 and 2. In today's session, I'm going to discuss the same paper, but question number 3 and 4. And please watch the complete video so you people will be able to learn some extra points as well. Let's start from question number 3. So according to this question, phosphorus, phosphoric 5 acid. H3PO4 is the phosphoric 5 acid because the oxidation state of phosphorus in this acid is +5. So that's why it is phosphoric 5 acid. It is used in both inorganic and organic reactions. So H3PO4 is made in a two-step process from phosphorus. Step one is that phosphorus reacts with an excess of oxygen. So this is the important point that you have the excess oxygen. So you have to make the compound with the maximum oxidation state of phosphorus uh, to form white solid. The white solid, which is formed as a reaction of phosphorus and oxygen, that further reacts with water to form H3PO4. So write an equation. So you have to write down the equations of both these steps. The first equation is that when phosphorus reacts with oxygen, so this is phosphorus. If it reacts with the excess oxygen, you will get P4O10. Although you may get P4O6 as well, but as we can see that in the step one, because the excess of oxygen is used, so that's why you have to make the oxide of phosphorus, which have its maximum oxidation state, like +5. So if we balance this chemical equation, there are 4 oxygen atoms and 4 phosphorus atom and 10 oxygen atoms. So this is the balanced chemical equation. Now the white solid, this is the white solid, and when it dissolves or reacts in with water, so P4O10, when it reacts with the water, you will get the product of the same oxidation state, and P4O10, the oxidation state of phosphorus is +5. How? Like there are 4 phosphorus and then 10 oxygen, and the sum of is 0 because the sum of oxidation states in a compound is 0. We know the oxidation state normally the oxygen has -2, so this is -2, so the sum is -20. So if we put +5 here, we will get the +20, so that's why the sum will be 0. So in this compound, the oxidation state of phosphorus is +5. So we have to make that product in which the phosphorus has +5 oxidation state, like H3PO4. So H3PO4, there are 3 hydrogen, then 1 phosphorus, and then 4 oxygen, 0. This is -2, and hydrogen is always +1, except a metal hydride. So this is +3, and this is -8. So -8 +3 -5. So here you can put the +5. Although some of the students may think that we will get H3PO3, but H3PO3 will not be formed as the oxidation state of phosphorus will be +3 in that compound. So that's why you have to make that product in which the phosphorus has +5 oxidation state. Oxidation state will not change. So there are 4 phosphorus, so you can put 4 here. Then 12 hydrogen, you can put 6 here. 10 and +6, 16 oxygen. So 4 times 4, 16 oxygen. So these are the 2 balanced chemical equations. In the next part, H3PO4 is a weak Bronsted-Lowry acid. So define weak Bronsted-Lowry acid. Acid, is the substance which is a proton donor. And weak mean that the partially ionized. So if we want to define the Bronsted-Lowry acid, mean the weak Bronsted-Lowry acid. So acid is a proton donor. Acid is proton H positive donor. So this is the definition of acid, and it partially dissociates in an aqueous solution So it will be the weak acid. So it partially dissociates in aqueous solution. So this question has 2 marks. Uh, if a student write that partially dissociates in aqueous solution, then he or she will get 1 mark. But you have to define the acid as well. Acid is a proton donor, and weak acid is the acid which partially dissociate in the aqueous solution. Now, this is another part that H3PO4 is also formed in the process shown in the reaction 1. This is the reaction 1. So in which we are getting the different products, shows some relevant thermodynamic data. So the enthalpy change of formation of all these compounds is already given. So the question is that define enthalpy change of formation. Enthalpy change of formation is the enthalpy change when 1 mole of compound is formed. When 1 mole of compound is formed from its constituent elements in their standard states. You can also say the under standard conditions. So that will be the standard enthalpy change of formation. So this is the definition of standard enthalpy change of formation or enthalpy change of formation. Let's move to the next part. Use the data in the table 3.1 to calculate the enthalpy change delta H reaction of the reaction 1. So the reaction 1 is already there. Just have a look. This is the reaction 1. So if we copy the reaction 1 in this part, that this is H3PO4 that dissociates from H3PO3 and then PH3. PH3 is a phosphine gas. So this is the balanced chemical equation. So in this question, we have to calculate the enthalpy change of reaction, means you have to calculate this thing. And the given data is regarding standard enthalpy change of formations. So formations mean when the 1 mole of the compound is formed from its constituent elements under standard conditions. So to make H3PO4, we have to require 3 reactants: hydrogen, phosphorus, and oxygen. So we will get H3PO4. So these hydrogen, phosphorus, and oxygen, they can also make H3PO3 as well, and the phosphorus and hydrogen can make PH3. As we're getting the 4 moles of hydrogen, so don't no need to balance this hydrogen of phosphorus and oxygen, because these 3 reactants actually they are using on the left and on the right hand side, but just concentrate on the moles of the product which you people are getting. So the standard enthalpy change of formation of H3PO4 is the 4 times. So you can put the data 4 times here. And the standard enthalpy change of formation of H3PO4, H3PO3 is, let's just have a look. This is H3PO3 and on the right hand side, H3PO4. Okay, so this is H3PO3 and this is H3PO4. Okay, so you have to put the correct data. So H3PO3 is H3PO3 minus 972. So this is minus 972 4 times. And then H3PO4 minus 1281. This is 3 times, minus 1281. And as we are getting the 1 mole of PH3, so the standard enthalpy change of formation of PH3 is 9. So just put that at 9. So this is the triangular form of Hess's law, as we can define the Hess's law as the react enthalpy change is independent by the route which is taken for the chemical reaction. Or if a reaction takes place in one step or in several steps, the overall enthalpy change will remain constant as long as the initial and the final conditions are kept constant. So there are two ways, like if we can start from here, and this is the starting point, this is the end point. So this is the one route, and then this is a second route. So the enthalpy change in the first route is exactly equal to the enthalpy change of second route. So there are two changes in the second route and two changes in the first route. So x plus 4 times minus 972. This is the second route, and that is exactly equal to the first route, which is 3 times minus 1281 plus 9. So this is x minus 4 times 972 is 3888 is equal to 3 times this is 3843 plus 9. So x will be minus 3888 is equal to minus 3834. Then x is minus 3834 plus 3888. So if you solve this, you will get the answer 54, which is in positive. So this is the way that you can get the enthalpy change of the reaction by using the data regarding enthalpy change of formations. So you can take help from the triangular form of the Hess's law to do this calculation. I hope you will get my point. Then explain why reaction 1 is the disproportionate. Disproportionate reaction is that reaction in which the same species both oxidized and reduced. So if we look at the enthalpy changes of the reactants and the product in the above equation, now H3PO3, the enthalpy change of first the oxidation states, hydrogen is +1, this is +3, and this is -2. Here the hydrogen is +1, and the phosphorus is +5, and this is -2. Hydrogen is always +1, so this is F +1, this is -3. So as we can see that the oxidation states of hydrogen and oxygen, they remain constant, but only the one element is changes its oxidation state, like phosphorus on the left hand side, it is +3. So some of the atoms of the phosphorus, they change their oxidation state from +3 to +5, mean oxidized. And some of the phosphorus atom, they change their oxidation state from +3 to -3, which is the reduction. That is disproportionate reaction because the same species phosphorus is oxidized and reduced in this chemical reaction. So we can say that phosphorus in H3PO3 is both oxidized and reduced simultaneously, or at the same time. I mean, phosphorus oxidizes from +3 to +5 oxidation state, and it reduces from +3 to -3. Because the same element is both oxidized and reduced, so that's why this is the disproportionate reaction. The oxidation state of the other elements, that is constant. Now, this is the question regarding organic chemistry. So this reaction, there are a lot of reactions, but this figure 3.1 shows a reaction scheme that involves H3PO4 in several reactions. As you can see that this is, that this is alkene, and A is a substance which is used and in the presence of acid, and we are getting the alcohol. whenever we get the alcohol from the alkene, that is the hydration, and here you can use the steam. A is a steam, so you can use steam. Now this is alcohol, and this is a 2-degree alcohol, and 2-degree alcohol or secondary alcohol is oxidized to ketone. Primary alcohol is oxidized to carboxylic acid, but this is a 2-degree alcohol, or secondary alcohol is oxidized to uh, ketone, and this is ketone. And here we can use the oxidizing agent, like we can use the acidified K2Cr2O7 or acidified potassium permanganate or potassium manganate 7. This is a reaction. Then this alcohol is converted into ester. As you can see that this is the ester, and we're getting the ester, but when this alcohol is reacted with the acid, so it's CH3COOH. When it reacts with the alcohol, ethanoic acid, when it reacts with the alcohol, you can say this process is esterification, or you can say this is condensation. And when you get the ester, that definitely you have to remove the water. But if you copy this alcohol, that this is the alcohol, and you can remove the hydrogen from the alcohol, and OH from the acid. Like if we have this CH3C double bond O, OH, this is the ethanoic acid, and the alcohol is secondary alcohol, as we can see that this type of alcohol is there. This is the alcohol. So if you remove the OH from the acid and the H from the alcohol, you will get a product like CH3C double bond O, and then this is the ester linkage, and then you have the uh, part of the secondary alcohol. So if you convert this formula into a skeletal formula. There are 2 carbons, so you can put 2 carbon, second carbon, double bond, okay, double bond, then there's oxygen, this is oxygen, then you have CH here, this is CH, then 2 alkyl groups, one on this side and one on this side. So this is the structure of this ester. And then this is OH, and when we react with the KBr and H3PO4, you will get a B. Okay, let's start from the question, then we will see that what is the product P. Identify the A. We have already talked about the A, which reacts with the propene in the presence of phosphoric acid in the reaction 2. This is reaction 2, and when you get the alcohol from the alkene, the reagent which is required, that is steam. So this is steam. Draw the structure of the B. Now alcohol react with the KBr, and when alcohol reacts with the KBr, this OH is replaced by the Br. So that's why just copy the reactant and replace the OH by Br. So here you will get the halogen alkane, which is also the 2-degree or secondary halogen alkane. Then name the type of the reaction that occurs in reaction 3. Just have a look of the reaction 3. Okay, we have talked about the reaction 3, that the reaction 3 is esterification or the condensation. So this is the condensation. The next part is about the reaction 3 is monitored using infrared spectroscopy. So this is the question regarding infrared spectroscopy. It is not possible to use the OH absorption frequency to monitor the reaction. So table 3.2 to identify. Now you have to use this table, which is given here. To identify a suitable bond whose absorption frequency can be used to monitor the progress in the reaction 3. State the change you would see in the infrared spectrum during reaction 3. So in reaction 3, actually, you have the 2-degree alcohol, and that is converted into this ester. Now look at the data. Now alcohol has okay, there is no data regarding alcohol, so you can't use the data of alcohol because you don't have the characteristic infrared absorption range of the alcohol. So to state the change, as you can see that in the alcohol, the OH bond is converted into C double bond O, but you have the data of C double bond O. So this bond actually can be used, or the data of the C double bond O can be monitored. Now, change in infrared spectrum. As you can see that the range of when you get the ester, the range is 1710 to 1750. So the absorption range to frequency of the wave number is from absorption range from 1710 to 1750. So this is the absorption range. You can use all the range of this. You can start from here, that 1640 to 1750. This is also okay. But more specifically, this is correct that because you are getting the ester, so that's why you'll have to specify the range as 1710 to 1750. That's better. Okay, now look at the next part. Now, H3PO4 also reacts with alcohol to form this organophosphates. Organophosphates are compounds similar to ester, and they have the general structure shown. So phosphorus, it has 5 electrons, so it is making a double covalent bond with one of the oxygen and 3 single covalent bond, and then there are 3 alkyl groups are there. So 3 alkyl groups are there, then 1 phosphorus is there, and then 4 oxygen are there. Complete the equation to suggest the product of the reaction H3PO4 with the methanol CH3OH. Now this actually H3PO4 also reacts with the alcohol. So this is a reaction of alcohol and H3PO4. So if you react this acid and alcohol, you will get the salt and water. Now, because there are 3 alkyl groups here, 3 alkyl groups are there, so 3 alkyl groups are there. So there are 3 oxygen as well. So you can write like this. There are 3 alkyl group and 1 oxygen. So if we make it 3 times, we'll cover CH3O3. So we'll get a product CH3 3 times, and then there is CH3O 3 times, CH3O 3 times, and there is 1 phosphorus and then 1 oxygen, and you will get another thing, water. So if we remove CH3O3PO from this thing, okay, so then H2O will be left over, and you can balance the number of hydrogen and oxygen atom by putting 3 here. So these are the products which we make it by reacting H3PO4 with CH3OH. Now the compound T is a simple organophosphate. The mass spectrum of the T shows a molecular ion peak. This is M peak. 182. This peak has a relative intensity. This is the relative intensity or percentage abundance of M peak. This is the percentage abundance of M peak. The relative intensity of M plus 1 peak. This is the percentage abundance of M plus 1 peak. Reduce the number of carbon atoms in T and hence suggest the molecular formula of T. Assume that phosphorus and oxygen exist as a single isotopes, so you can't change the mass number of the phosphorus and oxygen. Now, if you want to find out the number of carbon atom, there's a formula which can be used to find the number of carbon atom. So N is 100 over 1.1 times percentage of M plus 1 peak over percentage of M peak. Now, 100 is there over 1.1 times the percentage of M plus 1 peak is this, okay, 0.84 divided by 12.7 is the percentage of M peak. So if you calculate this, you will get 6.0. So the number of carbon atoms in T, they are 6. So there are 6 carbon atoms. As we can see that the MR of this compound is 182. So the 6 carbon atom, when this compound contains carbon, it contains hydrogen, it contains oxygen, and it contains phosphorus. So that is equal to 182. Now there are six carbon atoms, one oxygen atom, because phosphorus and oxygen exist as a single isotope. So there are one oxygen atom and one phosphorus atom. So the share of the carbon atom is 12 times 6 is 72, plus 16 plus 31. So this is 6, 8, 9, and then 7, 10, 11. Yes. So if you subtract, there are, I think there are phosphates. So it means that there are 4 oxygen, PO4, yeah. So there are 4 oxygens, so 16 times 4. So you will get, okay, minus, we can minus here. 72 plus 64 plus 31. Okay, so if you subtract this, this is 182 minus 167, which is 15. So that's why the hydrogen atom must be 15. So this is the formula C6H15O4P or C6H15PO4. This is the phosphate, so that's why you have to keep PO4. So the molecular formula of T is there are 6 carbon atoms, 15 hydrogen atoms, then 4 oxygen atoms, and then 1 phosphorus. Okay, so next question. Lactic acid, this is lactic acid and pyruvic acid, both contains 2 functional groups. Explain why lactic acid exists as the optical isomers. Optical isomerism is the type of stereoisomerism which contains chiral carbon. So chiral carbon is that carbon which is attached with the 4 different groups. So if we look at the lactic acid, so lactic acid, you can see that the lactic acid, it is attached with 4 different groups. So this lactic acid contains contain chiral carbon, and whenever the molecule exists as a optical isomerism, it means that if it contains chiral carbon, so you can say that it can also these show they will show the they are the mirror image of each other. So give the systematic name of the lactic acid. Okay. So the lactic acid, first of all, select the longest chain. This is propane, and this is carboxylic acid. So propanoic acid. But this is the first carbon. This is the second carbon. So this is hydroxypropanoic acid. But the hydroxy group is present on second carbon. So that's why it's better to write 2-hydroxypropanoic acid. So this is 2-hydroxypropanoic acid. Then the next part, lactic acid form hydrogen bonds with the water. Complete figure 4.2 to show the formation of hydrogen bonds between 1 molecule of lactic acid and 1 molecule of water. As we can see that for the hydrogen bonding, hydrogen must be attached with the more electronegative atom like fluorine, O oxygen, or nitrogen. Hydrogen must be attached with the more electronegative atom. So as we can see that this hydrogen is attached with more electronegative atom oxygen, this hydrogen attached with more electronegative atom oxygen. So this is the partial positive end, this is the partial negative end. We can also say this is the partial positive end, this is the partial negative end. So if we want to make the hydrogen bonding, water is also a polar molecule. So water being a polar molecule, it exists as a this is a non-linear or V-shaped or angular shape. It has 2 lone pairs. So if this is the partial positive end, now the oxygen can make the hydrogen bond with it. Here you have the partial positive, partial negative. This is also partial negative. And here you have to show the lone pair. So the hydrogen bonding is the electrostatic force of attraction, which is present between the lone pair of oxygen and partial positive end of another molecule, and which is definitely hydrogen. So here you can show the hydrogen bonding. So this is the hydrogen bonding between two hydroxy propanoic acid and water molecules. Here you can also see, because he's saying one water molecule, so you can show another water molecule as well, which can make the hydrogen bond with this OH group as well. Now, the next part. Now, two possible syntheses of the pyruvic acid are shown in figure 4.3 and 4.4. Each synthesis has a total of 3 steps. We can see that the propene here is converted first. This is the first step. So propene is converted into halogenol alkane. So we are reacting with the Br2 in the first step. Okay, so alkene is converted into halogenol alkane. So this is the reactant. Now, halogenol alkane is converted into another here. You will get another substance. And in the third step, when that substance is oxidized, you will get the this acid. Okay, so if you draw the structure of this acid, you will get that there is a ketone as well. This is C double bond O ketone, and then the carboxylic acid is also there. You know that the ketone is formed from 2-degree alcohol, secondary alcohol. So it means that here, if you draw the structure of a substance, it must contain secondary alcohol, and carboxylic acid is formed from the 1-degree alcohol, because there's oxidation. So from the oxidation, we can check that this oxidation, in the case as a result of oxidation, you're getting the ketone and carboxylic acid. So ketone can be obtained by oxidizing the secondary alcohol, and the carboxylic acid can be obtained by oxidizing the primary alcohol. So it means that in the step two, you must have a substance like that. If we copy this, this is the substance. So if we put OH here, this is the 2-degree alcohol, and if we put OH here, this is the 1-degree alcohol. So you will get a product like this, and when this is oxidized, you will get this thing. And in the second step, halogenol alkane, they can be replaced by the OH when you react halogenoalkane with aqueous sodium hydroxide and heat under reflux. Then in the third step, there is oxidation, and for the oxidation, you can use the acidified KMNO4, which is the oxidizing agent. So this is the complete scheme of this 4.3. That propene, when it reacts with the bromine, you will get halogenol alkane to alcohol by the aqueous sodium hydroxide, and then from alcohol to ketone and carboxylic acid from oxidation. Now, in the second scheme, 4.4, now, and there's the ethanol, and in the ethanol, in the first step, you're getting something here, and then in the second step, you are getting this thing. So if we draw the structure of this thing, like this is CH3, and then CH, and then OH. This is again secondary alcohol, and you're getting C double bond O OH. This is carboxylic acid. So carboxylic acid, as you can see that the carboxylic acid is here. So we're not changing the carboxylic acid here, but secondary alcohol is oxidized to ketone. The same is the case that when you have the secondary alcohol here, you have the secondary alcohol here, you can use the same thing. Means secondary alcohol is oxidized to ketone. This is the ketone, because we're getting the same product, like, yeah. So ketone, or secondary, here must be a secondary alcohol. So this is the secondary alcohol. So how can you get the secondary alcohol from aldehyde? Let me draw the structure. This is a aldehyde, C double bond OH. Okay. So if we react with HCN in the second step, in the first step, yeah. So if we react with the HCN, So by reacting with HCN, we will get a product like this. You have to copy this, just break the second bond. Okay, so just add HCN here, H and then CN. Okay, so this is hydroxy propanonitride. Okay, now you have, I think, learned both the synthesis route 4.3 and 4.4. Now let's talk about the questions. Okay, so before doing the question, you can stop the video and you can learn this stuff, and then you can comfortably solve your questions. Uh, Complete the diagram for mechanism for the reaction propene with bromine. Okay, so to draw the mechanism, uh, this bromine is polarized in the presence of double bonds. So the end, which is close to this bromine, it must be partial positive, and which is away, that must be partial negative. Then there's an attack from this double bond to bromine. So you can show the curly arrow. Then there is a hydrolytic fan. So as a result of hydrolytic fan, you will get the Br negative, and you can show the lone pair as well. So just copy this thing without double bond. Okay, so if this double bond, one of the bond is broken, and if it attacks on bromine, you can show the attachment of the bromine. One of the bromine is attached with here with this carbon, and the very next carbon, it must be positive. I mean, this is the carbocation. Now, this bromine, Br negative, that will attack on the carbocation to form the final product. We're getting the final product. This is the final product. So you have to show the partial positive, partial negative, then the attack from the double bond, then hydrolytic free, then Br negative with the lone pair, carbocation. Bromine must be attached, and then another curly arrow, which shows the attack on the secondary carbocation. So then you will get the 3 marks. Okay, so basically you have to show the charges. We have shown the charges, then the dipole, yeah, the dipole as well, the lone pair, electrons, lone pair. Okay, so you have to show all the things, charges, dipole, lone pair, electrons, and sorry, the curly arrows as well. Then in the next part, write an equation for the oxidation of lactic acid to this acid, and the third step, I think we have already talked about this, that use O to represent one atom of the oxygen and then oxidizing agent. So oxidizing agent is oxygen donor. So you can represent here oxygen. This is a secondary alcohol. If you want to learn it completely, let me draw the easy structure for you people. Okay, this is actually the thing. It contains, this is hydroxy, 2-hydroxypropanoic acid, and when it is oxidized, because this alcohol is 2 degree and it must be oxidized to ketone. So here you have to show the ketone. Now this is the carboxylic acid. Carboxylic acid is not oxidized. So if we remove 2 of the hydrogen now, 2 hydrogen, then we will get a double bond here. Okay, so we'll get a double bond here. So by removing these 2 hydrogen, and if they combine with the oxygen, you will get water, H2O plus. So just you have to remove these 2 hydrogen, hydrogen. Okay, so just copy the product without these hydrogen. So CH3, then CO, and then COOH. This is the final product because you have the ketone and the carboxylic acid in this final product, and you have to remove the water as well. Okay, now let's see the next part. Complete table 4.1 to give details of the reagents and the conditions used in each of the 2 syntheses shown. So this is 4.3. Reagents and the conditions used. I think we have already talked about this. And this was the first step. In the second step, from the aldehyde, no, second step. In the second step, there was a reaction. Yeah. So aqueous sodium hydroxide is used, and in the third step, acidified KMnO4 can be used. So here you can use the aqueous sodium hydroxide, and here you can use the acidified KMnO4. Here you can also use the same reagent, acidified KMnO4. Now, in figure 4.4, what was the first step? 4.4. This was the 4.4. Yes, we have reacted with the HCN, or you can also use the KCN as well. KCN, because HCN is a weak acid and it partially dissociates to provide the maximum concentration of Cl negative. You can use the mixture of these two reagents. So we can use the HCN and KCN. Then in the second step, we can use the, just look at the second step. Okay, so this is the second step. In the second step, we are converting the CN to carboxylic acid. So this is the acid hydrolysis of CN or nitride. So acid hydrolysis means you have to use the acids. You can use the dilute HCl or dilute sulfuric acid. So this is all about the question number 3 and question number 4. I hope now you will be able to solve this paper independently. And please don't forget to subscribe my channel. In that case, you will get the latest videos. Thank you.